off my little veneering of my PFM. PFM breaks as well, not just all ceramic restorations. Okay, hackle. A hackle is a line on the crack surface running in the local direction of cracking. You see these lines here? Now the question is it running from top to bottom or from bottom to top? Well, in order to know that, you have to find little pores. In a veneering ceramic, you will be able to find pores, lots of pores. If you see a pore, you have to remember that the crack front will go, pass over the pore, and leave a trail behind it. This trail is this thing here. If you see a pore with a trail, it's called a wake hackle, which is a hackle extending from some sort of discontinuity. It can be a pore, it can be an inclusion, it can be anything that bothers the crack path. So in that sense, you know that the crack direction is from bottom to top. Very important feature in clinical failure analysis using fractography. Then there is a twist hackle. Twist hackle is a hackle which has rotated from the original crack plane in response to a lateral rotation or twist of the axis of principal tension. In essence, what you see are little Y's. It's like a fork, and it twists like this. So that's how it looks like on a veneering ceramic. As soon as you see a Y with a big tail, you know the direction of crack propagation. Higher magnification, you will see these forking, this Y thing, that's a twist hackle. An arrest line is a sharp line when a crack comes to a complete halt before resuming its propagation. Typically here, a tiny little chip on an occlusal surface of a very old Cerestor crown. So you see one arrest line, a second, a third, a fourth. It started here. This is wear, contact wear. The failure origin is always located on the concave side of an arrest line. So this is concave here, so the origin is somewhere here. So in essence, there are a certain amount of features that will be the key of success to know what's going on in clinical failures. Compression curl, arrest lines, hackle, mainly wake hackle, and twist hackle. There are a couple of publications you can read back in which we have described with examples. But let's have a look at the real case. And by the way, this was the first, I would say, complete case that we were allowed to publish thanks to David Watts from Dental Materials, who took the fractography course, the first one in 2007, enjoyed it very much, and allowed us to publish a paper that was based on one single case to describe the technique of systematically mapping and of a systematic approach of a failure of a real crown. And that's something we're going through right now. In essence, you have a piece. You always have to look at it under a stereo microscope first, with trans illumination, light illumination from the side, and then only you go to the scanning electron microscope. You have to label your piece with numbers. You start here, 1, 2, 3, 4, 5. These are zones of interest. You have to specifically look at these areas to have a global picture. And you have to label what's a veneer, what's a core material, and definitely you have to label if this is distal or mesial or occlusal, because an engineer does not know what a crown looks like. And it's very complicated. Sorry, but that's what George told me. I don't understand anything. Tell me left, right, distal, mesial. So he wanted to label everything. And then, excuse me, in parallel, we look stereo, we see a little chip, and on the scanning electron microscope, we see a marginal chip. If we go at higher magnification, we see arrest lines. At higher magnification, we see wake hackle. So this chip started from the margin and popped out right there. It's not very big. It's about 2 millimeters in length. And then we move to the flat side of the crown. And remember, we are going to move over the whole surface and try to recognize features. And these features, for me, the easiest ones are the wake echo. As soon as I see a wake echo, I know the direction of crack propagation. So you start recognizing them. Sometimes you have to go to 500 times magnification. Sometimes you have to go to 1000 magnification. If you're very good with transillumination, you can even see them with a stereo microscope that goes up to 200 times magnification. So here it goes up. If I go to this area, it's more complicated, but you see on the stereo microscope, you see these faint lines here. Under the scanning electron microscope, it's more complicated. You don't see so many of these lines. That's why you always have to do this in parallel. But in essence, the crack moves. This is a little wake echo. It moves to the right, or if you wish, from here to the right. And then you get to the compression curl, and you want to make sure that if this is a compression curl, the crack will move to the outside, to the right side. So you have to zoom, and sure enough, you'll find a wake echo. So it's mapping, it's evidence, there's no invention. You just have to be patient and do this slowly. Now, we'll become suspicious about this area, and I'm getting there. What is this? I told you before, there is a rest line, and the starting point of a chip or a damage is on the concave side of a rest line. So this time we're talking the occlusal surface. A rest line, a rest line, a rest line, a rest line. And at higher magnification, twist cycle, everything moves from top downwards. But the crack stops right here. It never went beyond this arrest line. This crack front was much more powerful, so this is definitely the prime reason for failure, and this is a secondary event. And that's why it's very important before people say, oh, it started from the occlusal side because I saw a chip. No, you need to show me the evidence, which one came first. And with a little bit of patience, with a lot of time under the microscope, this is the occlusal surface, the little chip here stopped right here. The other crack front is moving this way. And so definitely this is a secondary event and not a primary event. So at the end, you map everything, you come up with a little story, and it's not always easy to know why it failed. This crown, by the way, failed after 4 years. It didn't fail after 2 months, 4 years. The fracture started from an edge chip on the mesial margin of the veneer. From the chip, hoop stresses propagated the crack along the axial wall, then moved over the occlusal side and ended up on the distal side of this palatal second premolar. More than that, we will not have an information. And clinical dentistry will never be as pretty as a bend bar that shows you a real flaw with a real size. It's much more subtle. Exercise, number 2. 5 years. It failed after 5 years. It's one of a colleague of my class roommates that called me a few months ago. Susanne, I have a 5-year-old Illumina crown. Would you like to have it? I said, yes. When I get a crown, I get very hyper. I'm like Bob. It makes my day. I'm really happy. I'm going to spend 40 hours to understand why this thing failed. Okay. So this is an Illumina crown. I don't know which veneering ceramic it is, but I believe it's Nobel Rondo at that time. Systematic approach. We start from one side, we finish on the other side. Number 1, I focus on the veneering ceramic. And what's the name of this? Wake echo. Direction goes from bottom to top. This is the Illumina core material, so you all agree it goes up. Number 2, you already can see lots of little fainted lines here, okay? But we need the detail. or pour with a little tail. Hackle. Twist hackle. More or less that direction here. Here, this big pour is this one here. Beautiful wake hackle. It goes up, outside. Number 4, to the right. It's veneering ceramic of all ceramic restoration is great because it's lots of glass. So it's very easy to see. So, okay, something becomes then suspicious because it must have started somewhere here. So then we focus on the margin. What do we see there? Well, there is a little chip, but look more closely in this area. I'm going to zoom in. What is this? Unfortunately, my dental school is not rich, has a very old scanning electron microscope with no elemental probe. So I cannot tell you what is this. What I can tell you is this is not normal. This is not a classic alumina. It's a dense alumina, supposedly a dense alumina. It looks weird. There is some contamination. There is something on that margin. And if I go back, this is approximately 40 micrometers in size. And it's at the tip. And definitely this was the reason for failure after 5 years. 5 years is far too early for an all-ceramic restoration, at least for Swiss standards. It should last a minimum of 15 years. Okay, try-in failure. That also happens. It's good because there is no plaque, there is no dirt, you can work with it. It happened to my dear colleague, Francesca, who used to work at Connecticut. And she's very good in photographing everything, so she gives me these pictures so I understand what she's talking about. And then she gives me this picture, and so I analyze that piece of broken alumina crown over a zirconia abutment. In the meantime, I hope you recognize lots of little features. Compression curl, arrest lines, hackle, arrest line, hackle or wake hackle, I don't know. Margin is terrible. And then I see some hackle down here. So we start to map zone of interest 1, 2, 3, 4, 5. And we are suspicious about certain things here, here, and here, which are in red. But we have to be systematic in our approach. So we look at one margin first. And if we magnify, we can see very fine hackle lines in the alumina material. And then we see the Y here, which is the twist hackle. So the direction is very clear. It goes from the inside outside. If I rotate the microscope and I look at this, it looks a real arrest line. So definitely there was some zone of stress concentration at that margin. And I would like to point out that this is a 200 micrometer scale bar. And these CAD/CAM machines can machine down to something extremely narrow. It's amazing. This is less than 100 micrometer thin at the margin. And Rosetti, this is for you. Please do me some finite element to show me that this is terrible. I would be very happy to have that information. Anyway, the crack moves up. So if I see something here, I go right away to the other end. I want to know. I need an evidence that goes outside to the left. Or if it goes up here, then I have two origins. I have two margins from which it failed from. And lucky me, a beautiful wake hackle that moves from inside outside. So then you just become more fancy and you try to see, okay, the direction is here, the direction is here. I can zoom this area here. I have all the evidence I need. I have an arrest line. Here, there is something weird. What is this? I'll tell you later in a minute what that is. It's a chipping off the alumina, and you'll understand later on. I'll come back to this chipping off. Just remember, there is a chip off of the inside of the alumina crown that is